monitored. There has to be some type of indication that indicates where there is a ground fault or why there's a ground fault. However, the most common type is indicating lights, where somebody can visually look at a series of lights, and by the lights being bright or dim, it will tell them they have a ground fault on the system. However, it doesn't tell them where there is. There's not an effective technology today for one to automatically detect a ground fault in a specific location. In an ungrounded system, you actually have to take a clip-on ammeter in the course of pulsing the system. We actually induce a pulse on the system, and you take a clip-on ammeter down a line of conduit or inside equipment to determine where this pulse stops or ends. Or you're going inside and looking inside equipment, looking for arcing faults. It's very time-consuming and it's very expensive. And oh, by the way, it can expose the people that are doing the detection, the investigation, to transient overvoltages if your system is not effectively bonded together, which is one of the reasons we don't recommend them. Where they're predominantly employed is in industrial applications, petrochemical plants, pulp and paper plants, where a phased or ground fault would shut down a system very, very rapidly. And they'll use ungrounded systems, and they also have trained people there. If you're going to have an ungrounded, if you're going to employ an ungrounded system, be it a Y or a Delta in a data center, you need to have trained people, one, to install them, two, to be able, readily available, to find where the faults are and get them off the line as fast as possible. What often occurs where you have an arcing ground fault is that the transient overvoltage is so high, it begins to break down the insulation of the other conductors that are not associated with fault. Consequently, you end up with a phase-to-phase fault very, very rapidly. And then your breakers will operate. By that time, you've had quite a bit of damage done. In data centers, one of the reasons we don't recommend them is that data centers are not manned 24 hours a day. And when they are manned, they do not have trained people on staff 24 hours a day with the tools available to go search for an arcing ground fault if one were to occur. Now, more industrial processes like petrochemical plants and pulp and paper plants do have such people on staff that are trained. It's a specific type of art. In addition to ungrounded systems, your grounding and bonding systems have to be regularly maintained and regularly inspected. Very, very important. That's rarely done, which, again, is another reason for not having them. The other type of system is a three-phase, four-wire, solidly grounded system. This is the system that began to occur in North America, specifically the United States, beginning in the late 1950s. And by the 1960s, many of our systems were converted to three-phase, four-wire, solidly grounded systems. And the reason for that was at the time we were converting a lot of our lighting inside our buildings from incandescent and fluorescent. We needed to conserve energy in this country. We began making transformers. Instead of having three separate transformers and connecting them together externally, we began putting all of the transformers inside the same tank, where you would have a three-phase transformer inside one large enclosure. This saved real estate, it saved materials. But the primary reason for going and converting from ungrounded systems to a solidly grounded system, such that our utilization voltage was 270 or 40 volts Y, 277, three-phase, four-wire, is that the 277 volt utilization voltage allowed a large enough voltage or a high enough magnitude of voltage to power metal halide lights or gas lights. For example, low pressure sodium, high pressure sodium, metal halides, mercury vapor at the time. You need a high enough voltage in order to strike through the arc. Our typical voltage at the time, where we had lighting receptacles or lighting in a building, we would take 40 volts off a three-phase, three-wire and go through a separate lighting transformer where we would go from 40 volts, we'd convert that to a single-phase circuit of 120/240, and we'd drive our receptacles and overhead lights. A lot of the the lighting inside of a building, even though they had incandescent, they used incandescent, but they had fluorescent fixtures. Many of the ballasts operated on 120 volts. By using 277 volt lighting to operate the fixtures in the ceilings or in a facility, you could use a higher voltage at a lower ampacity. That saved wire, saved copper. Also, you had a high enough voltage to drive the voltage through a gas. So you could have more efficient lighting, less current, as an energy saver. That was the principal reason. However, what began to occur, we need to stop. What began to occur when we started converting, wait a minute. What began to occur when we converted our industry to three-phase, four-wire, 40-volt Y277s is that before with the ungrounded systems, if a phase to ground fault occurred, there was not a lot of current to flow to cause a fire. There was not a lot of high arcing current, though you did have transient over voltages that would break down insulation, causing subsequent fire or damaged equipment. You did not have a massive amount of current to flow, much like a welding arc. When we converted our power systems to three-phase Y277, three-phase four-wire, we got the benefit of being able to use the 277-volt phase-to-neutral leg, or the single-phase load off of that, to drive our lighting panels. Very easy, very effective. We avoided the cost of putting in another lighting transformer to operate our ceiling lights or our outside parking lights. That's a cost savings. Installation requirements were a lot less. However, the drawback that occurred is now when you have a phase to ground fault, you now have the destructive arcing ground fault condition. And many buildings caught fire, many people were injured, and some were killed as results of arcing ground faults, as a result of 277 volt lighting. That brings us to the point of, we said earlier that the codes lag behind the technology. Prior to 1971, we had three-phase, four-wire power distribution systems, but there was no code requirement for ground fault protection. There had to be a means to protect the circuits from these arcing ground faults, and that brought in the development of ground fault protection, beginning in the National Electrical Code in 1971. Prior to that time, all overcurrent protected devices were predominantly fuses and circuit breakers. As a matter of fact, Square D got its origins as a fuse company. Most people don't realize the origins of the Square D started back in 1888 with the McBride Fuse Company and began taking over as the Square D Company in 1908. We became the Detroit Fuse Company. Our fuses that we manufactured were revolutionary at the time. They were very durable, very rugged, and could be replaced. Now, they were manufactured in Detroit, and the tubing of the fuse link was actually a square. It was a square fuse. So people would call out for our fuses, and they would say, I want one of those square Detroit fuses. And later, the abbreviation got abbreviated to a Square D fuse. The D means Detroit. We were also the first one to bring in the fuse disconnect, where we actually had a means of replacing and operating a switch with our fuse disconnects. We could actually put a fuse in there. We had a disconnecting means. We can open up the disconnect if the fuse were to open and replace the fuse safely. The safety disconnect switch were developed by the Square D Company for our Square D fuses. The problem with fuses is at the time we were developing the fuses, our power distribution systems, as I said earlier, were three-phase, three-wire, ungrounded systems. The predominant type of fault at the time was a phase-to-phase fault or an overcurrent. Fuses are thermal magnetic devices. The fuses protected you from an overload, the thermal function. And most of the faults where the fuses would operate would be a phase-to-phase fault where you'd have two conductors touching. That provided enough energy to open up the link of a fuse. However, historically, all faults, predominantly between 95 and 98%, depending on which study you're studying, are phase to ground faults, have always been phase to ground fault. Fuses